Welcome to the first video for the projectiles topic. In this video we'll look at the maths behind projectile motion and look at some basic problems. So, in the projectiles topic, this is the sort of thing we're looking at. Objects being hit or thrown and travelling through the air, following some sort of arc. As we've seen before in the quadratic topic, these projectiles will always follow a parabolic trajectory. So these are quadratic curves, and we will actually have solved problems like these back in the quadratics chapter, but in this topic we look at how we can apply SUVAT to solve these problems. Now, the way to look at a projectiles problem is like this. We look at it in two ways. We consider the motion of the object, such as this golf ball flying through the air, as if we're either looking at it from above, so a bird's eye view, or as if we were looking it dead on, as if the ball was being hit straight towards us, such as this fella in the reclining chair will see. So if you consider the bird and what the bird is seeing, all the bird will see is a ball setting off from here and then moving to here and then stopping. It won't necessarily be aware of the fact that the ball is going up and then coming down. It will just see that horizontal motion as it moves from one point to another. So to model that motion, we can just use SUVAT, considering all the horizontal aspects of it, all the horizontal components of that motion. Whereas the fella over here, what can he see when he watches that golf ball set off and then finish? All he sees is the motion that the bird didn't see. He sees the ball rise, he sees the ball fall. He's not necessarily aware of the fact that the ball is coming towards him. So that's how we can split these problems up into the horizontal motion that the bird would see, and then the vertical motion that the man would see. On the first page of the booklet is this rather complicated diagram. This just kind of summarises everything we're going to do. But in the box there, it says what I've just described. That for the horizontal motion, we'll imagine what the bird is seeing, a bird's eye view of that motion. And for the vertical, imagine seeing it head on. So all you're aware of is that it's going up and down. So all of our models in this chapter will be based on the object being a particle and all the consequences of that, and then it's being acted on by only one single force, gravity. So gravity alone is acting up and down. There's nothing else acting on it, so we're going to ignore any air resistance, as we do when it's a particle, and any spin and the effect that would cause. Again, that's the consequence of it being a particle. And we're also going to ignore wind or any other external factors. And as I've said already, we consider it separately. So if we just consider that for a moment, if gravity is the only force acting on this particle, then we can see what the effect of that is on the SUVAT equations. So if we just consider horizontal motion, and this is how I write it, I say that I'm resolving horizontally, I'm considering just horizontal motion. Well, gravity only acts vertically. On this diagram, gravity will be acting down and not affecting anything in a horizontal way. So if we consider all the SUVAT equations, which I'll just quickly jot down, hopefully you remember all these. So those four, and then the one that I never use is this one. So since gravity is only acting vertically, and no other forces are acting horizontally, that means nothing can be causing this object to accelerate or decelerate. So the acceleration must be 0 in the horizontal considerations. So what does that mean for each of these equations? Well, this first one, if a equals 0 in this first one, all we get is that v equals u. So the final velocity at any point that we consider is equal to the initial velocity in that direction. That makes sense. If there's no acceleration, there'll be no change in speed. In the second one, if a is 0, then we're just left with the equation s equals ut. An equation you've been using for a very long time, even back in high school. Distance equals speed times time, essentially. This next one, if a equals 0, we just get v squared equals u squared. So once again, v equals u. I'll just go down to the last one. If a equals 0, we get s equals vt. But since v and u are the same, that's just the same as s equals ut. Since in all of these, v is equal to u. And then the one I skipped doesn't have acceleration in it, but the u and the v, as we've seen, are equal to each other. So all we get there, if we replace the v with a u, is 2u over 2 times t equal to s. So once again we get s equals ut. So what this means is whenever you're considering horizontal motion, you don't really need to think about the Suvat equations at all. There's just one equation that applies in all horizontal motion parts of a question. It's always s equals ut. So when you're considering the horizontal motion, you can still consider all the Suvat equations, or you can just always jump straight to s equals ut. That's only horizontal. Vertical, we've got to take gravity into account, so a will always be equal to the value of gravity, 9.8, positive or negative, depending on how we've assigned our positive direction. Okay, so if we're going to split our motion up into horizontal and verticals, we're going to have to split our velocities. I'll just run back to this golfer. When he hits the ball, he doesn't hit it horizontally, he doesn't hit it vertically, he hits it at an angle to the horizontal. So we call that angle the angle of projection. Sometimes labelled with an alpha, sometimes labelled with a theta, any other label will do. So what we're going to need to be able to do, if we're just going to split this into horizontal and vertical components, is calculate how much of this velocity is acting vertically and how much of this velocity is acting horizontally. So since the initial speed is labelled as a u, we often call that just u, sometimes a capital U. And then if we're resolving it into its verticals and horizontals, we might call this one uy, and we might call this one ux. So the x component of that velocity and the y component of that velocity. And then this one is the one that will feature in our s equals ut formula to calculate horizontal displacement. And this one will feature in any of the vertical calculations that involve gravity. So how do we find those? Here's a simplified diagram. I've got angle of projection of alpha, capital U for my initial speed, and then the uy and the ux labelled. Well, we just apply a little bit of a trig. If I just call this side uy, it's equal to the other side. And then I've got this side being ux. Then, just going back to basic trig, we know that sine alpha is equal to the opposite over the hypotenuse. So the opposite to the alpha is the uy. The hypotenuse is capital U. So we get uy equals u sine alpha. Something we've done before in vectors and other parts of the course as well. And then we can do the same with cos. Cos alpha is adjacent over hypotenuse. So ux equals u cos alpha. So it's best if you remember them as quickly as you can, because we'll be using those every time we are given a angular velocity and need to split it into its vertical and horizontal components, which will be most of the problems we see in this chapter. So, quick example of just doing that. We've got a initial velocity of 30 meters per second, an angle of projection of 42 degrees, and we're pretty much always going to want to be doing this to find out vertical and horizontal components of that 30 meters per second. So horizontal is just capital U cos alpha, so that's 30 cos 42, which is approximately 22.3 meters per second. That's if we rounded it. And then the vertical is capital U sine alpha, so that's 30 sine 42. Putting that in my calculator gives me 20.1 meters per second. Again, approximately. And this works because of Pythagoras. If we now use these two sides of our triangle, the vertical and the horizontal, to then work backwards to find out the hypotenuse, we would square these two values, add them together, square root, and we would get a value of 30. Okay, so that's how we split our initial angular velocity into its vertical and horizontal components. Sometimes I use the notation with the subscripts, the subscript of x and the subscript of y. Sometimes I don't. It depends how complicated the problem is and whether I need to really make it clear which bits are horizontal and which bits are vertical when I'm having to switch between them a lot. Okay, let's move on to some examples. So, in this first one, we've got a particle being projected. So, a particle, we know we're ignoring air resistance and rotation. It's from a point on a horizontal plane. So, it's starting on the plane and then ending on the plane, presumably. Hence why I've started my diagram off like this. And it has an initial velocity of 40 meters per second, and it's shot at an angle of alpha projected. That's an angle of alpha. So I can add on my initial velocity of 40 meters per second. I'll leave the units off to keep it more clear of a diagram. And then we've got our angle alpha. And then at some point I'm going to be working out those two things. Now we're not told alpha here, and what I don't want to do is I don't want to do the inverse tan of 3/4. That will give me an angle, but it won't be accurate. So whenever you're given your angle as a trig ratio rather than just the pure angle, the way to use that is to consider a right angle triangle. So this is a triangle representing this part of my diagram. So there's alpha in the same position, and then we know that tan is opposite over adjacent. So 3/4 means it must be 3 as the opposite, 4 as the adjacent. And then a quick bit of Pythagoras, or recognising a Pythagorean triple, tells us that that must be 5. So from that I can now use accurate versions of cos alpha and sin alpha rather than the inaccurate angle I would have got from inverse tan. Cos alpha being adjacent of hypotenuse, so 4/5. Sin alpha opposite of hypotenuse, so 3/5. So now when I calculate the vertical and horizontal components of that 40 meters per second, I can use the 4/5 and the 3/5 in place of sine and cos, and that's all we're asked to do on part A. So for the horizontal, as I said before, I usually write this when I'm writing down that I'm working horizontally, or you can just make it clear by using the subscript x for horizontals. So the formula to remember, very easy one, u cos alpha. U is our initial velocity, and then cos alpha, we've just seen is 4/5. So 40 times 4/5 is exactly 32. And then vertically, again, this is how I write it, or just using the subscripts is enough to show that you are working vertically. And this one's sine alpha times u. 40 times the 3/5 we got from the pink triangle. And that's exactly 24 meters per second. Okay, and that's probably how we will start off a problem, a more complicated problem. Finding those, probably leaving them exact. If they don't end up as exact, these are often decimal answers, so we'd want to use the exact one through the process of the problem. And then just putting in a bit of vectors, given that the vectors I and j are the unit vectors, as they always are, horizontally and vertically, it's asking us to express the initial velocity, that 40 meters per second, as a vector instead. Well, we know that a vector is just defined as its I component plus its j component, and we've just worked those out. The I component has magnitude 32, the j component has magnitude 24. So as a vector, so I underline my vectors, I could express that initial velocity as 32i plus 24j. Okay, and that's all there is to that example. Moving on, a little bit more going on in this one. As usual, we've got a particle. This time we're given a vector to represent our initial velocity. And then we've got to use those kind of in the reverse of what we just did to find the initial speed. So this value of u and its angle of projection, so the theta that I've already put on my diagram. So effectively what we've been told is that at the start there we're dealing with a right angle triangle with an angle of theta, and the magnitude of the adjacent is 3 and the magnitude of the vertical opposite is 5. We've been asked for speed, and when working with velocity vectors, we know that speed is found as the magnitude of the velocity, the magnitude of the velocity vector, which we will always get using Pythagoras, with or without a diagram showing that it's a right angle triangle. That gives us root 34 as our exact answer. We won't ask for an exact answer, so I would give a 3 sig fig one, with units for the context, and then for the angle we're just using trig. We were given the opposite and the adjacent, so best to use those rather than use the hypotenuse that I've just worked out. That angle must be the inverse tan of 5/3, which gives me 59.0 degrees to 3 sig fig. And when you produce an angle, always best to say where that angle is being measured from. 59 degrees could be measured from any direction. Is it from the vertical, from the horizontal, from a different angle of projection? Always best to say, and so for this one it is above that horizontal line. Not always necessary to write that, but often a good idea. Or we could say above the positive x-axis, above the horizontal ground, etc. Okay, third problem starts off a little bit different in that this part, again a particle, is projected horizontally. All the ones up to now have been projected at an angle. This one is being projected horizontally with a speed that we don't know. It is 125 meters above horizontal plane, so that's why I've started off my diagram with the horizontal line. So let's just add that to the diagram. 122.5 meters is that height there, and then it hits that horizontal plane at a point 90 meters away from where it started. So that length there is 90 meters. And we're asked to find the initial speed, which I'll just label as a u. Okay, so this is the first one we're actually going to have to do a little bit of suvat. Now, what I need to decide from a diagram ready for when I do the vertical motion calculations is which direction is going to be positive. I'm going to need to put gravity into the calculation. Gravity always acts downwards, but I will need to know whether it's a positive or negative, which is decided by the direction that I assign to be positive. Now, in most problems, I would be setting up as positive. I always decide to use the initial direction of motion as my positive. So this one, where the particle was starting here and heading upwards first, I would want up to be positive, meaning gravity will be negative. Same on this one. Starts here, heads in a upward direction first, so I would set up as my positive. In this one, however, the particle never goes up. It only ever comes down. So this is one of the few occasions where, for me, I would set down to be positive. Since gravity is then acting downwards, it has a positive value, and we know that gravity is 9.8. You could just use the same positive direction in all your problems and gravity will always be negative. That's perfectly fine. It's down to personal preference. Okay, so in order to find this speed, we are going to have to find out the time taken for it to travel that distance. Because for the horizontal motion, which we have information about, the 90 meters, we have s equals ut. If I can find out this u, then I've solved the problem. It is only acting horizontally, so the initial horizontal velocity is the answer to the problem. I know horizontally it's travelled 90 meters, but I don't know how long it took. So I'm going to need to find the time taken to travel those 90 meters. Horizontally I can't find that, but vertically I can. I have more information vertically. I have the distance, I have the acceleration. So I can use those two to find out the time taken to drop 122.5 meters, and then I can use that same time in the horizontal motion. So I know I'm going to be starting resolving vertically. I used this arrow to show in my maths which direction is positive. That's again a personal choice. You can do it all with the subscripts. And then this is now a SUVAT problem, so this is a good way to do SUVAT problems. Record all the information. So the displacement from the start is 122.5. The initial vertical velocity is 0 because it is not moving vertically at this point. Only from there onwards is there any vertical movement. The acceleration we know is positive 9.8 time is what I'm looking for, so I'm not going to need this velocity. It's not useful. So I need the SUVAT equation that does not involve v, and that is s equals ut plus a half at squared. So this is the equation of the quadratic, which would have been used back when we did projectiles in the quadratics chapter. We just didn't call it a SUVAT equation back then. So u is 0, so we've got a 0 for ut plus a half times gravity times t that we don't know. A little bit of rearrangement of that tells me that t squared is 25. So I get a nice answer. Doesn't always happen. It's travelled the full journey in 5 seconds. So now we can use that in our horizontal. So the only equation we have horizontally is s equals ut. I'll try and remember to use these subscripts. So horizontally, the displacement we know is 90 meters. U is what we're trying to find. It will be the final answer because it is the only component of velocity at the start. So dividing by 5 gives us 18 meters per second. And that's it because it was fired horizontally. If it was fired at an angle, we will need to find the vertical component and combine the two to find out the initial velocity, or initial speed, as it was asked for in this case. So if for some reason we'd got a negative answer because of the direction, we would not quote that as our speed. We would have to call it a positive value, as speed cannot be negative. Okay, that's the end of this section. If you want to practice the bits covered in this, then you can do so using exercise 6b from the textbook.